Hi everyone, welcome back. We're going to discuss cosmology today. This is going to be the first of two cosmology discussions. And cosmology is the last thing that we have to discuss in the course, so we're almost done. So cosmology is the study of the origin, history, and evolution and future of the universe as a whole. So some motivating questions. Why is the sky dark at night? That might seem like a strange motivating question, but you'll see why it's important. And of course, how did it all begin? How does the local part of the universe we observe relate to the visible universe that we observe from the light that was emitted billions of years ago? And how will it all end? And how do we know so much about the universe? And some kind of quick outline. So you'll have an understanding of some of the history of the subject as well as the observations that we've made and how general relativity fits into all of this. And we'll have a big discussion of the hot Big Bang theory and inflationary cosmology and some more recent observations and some of the trouble with the inflationary paradigm and some insights into the future of this field. So a couple of points of these extended. In terms of the history of the universe, we'll also talk about how things evolved from the Big Bang to the present day and the future of the universe as a whole, at least possible futures. Now, first of all, any troll who uses the word cosmetology when they mean cosmology automatically gets an F. So all their grades will be changed to F and they're done for the course. Anyway, so the words cosmology and cosmetology, even though they obviously refer to completely different ideas, they come from the same Greek root word cosmos, which means harmony and order. So while cosmetology brings harmony and order to your hair, cosmology seeks to bring harmony and order to the universe and our understanding of the universe. So in terms of beginnings, these beginnings lie in ancient times. A lot of these come from ancient religions and mythologies, which themselves were often born from various astronomical events. In other words, for example, interestingly enough, about 2,000 years BC, there was a very bright supernova explosion. At least we have found the remnant of what should have been a very bright supernova explosion that would have been easily visible, probably as bright as the full moon, to people, say, about 4,000 years ago or so. And it's quite interesting that a lot of the world's religions arose from around that time. And a lot of this history has been discussed previously in the course, but with that in mind, we're going to fast forward into the 19th century. So, of course, here we are in the 20th century talking about Albert Einstein, but we're going to backtrack a little bit, as you're going to see. So Einstein derived his results for general relativity, but when he did so, he realized that they implied the universe itself could not remain static, or else it would be unstable. Einstein and pretty much everybody else at the time believed that the universe was static. In other words, they believed that the Milky Way was all that there was, and they found no evidence that the Milky Way was expanding or contracting or anything like that. So to solve this problem, Einstein kind of added a term to his field equations of general relativity, this cosmological constant term, with the realizations like, okay, if the universe is actually static, but his field equations are implying that it must be expanding or contracting, there must be something that I missed when coming up with these field equations. So it must be that there's some inherent energy in space-time itself. So let's add in this cosmological constant term, or at least add it in and don't leave it set to zero. Apparently, I had been making this mistaken assumption that it was zero, and apparently it's not actually zero. So let's make that term non-zero in these field equations. And by doing so, this gives a kind of repulsive anti-gravity term to space itself. And that gives it this non-zero energy density and prevents something like, say, the Milky Way galaxy from collapsing. He didn't realize that the Milky Way was a composition of 400 billion stars that are actually all in orbit around a common center. They didn't have the observations yet on this. So Edwin Hubble eventually published results in 1929 showing that galaxies are actually moving away from each other. So when that happened, Einstein immediately realized that this cosmological constant was unnecessary, and he at times called it his biggest blunder. So this expanding universe actually presents a solution to an old problem. We're going to have more to say about the discovery of this expansion soon. I'm just kind of giving a quick overview right now. But Olber's paradox is this idea that if you were to look in the night sky in any direction, your line of sight should extend infinitely far. But if that's the case, then it should eventually land on the surface of a star. And that should be the case pretty much in any direction. So the universe, therefore at least the night sky, should be as bright as the surface of a star. Well, let's just say that that is not confirmed by observations. In fact, in calling this Olber's paradox, Olber's lived in the 19th century, but he kind of restated a paradox that had been stated a few hundred years previously. But Olbers himself believed that the solution to this was that there's intervening dust in our galaxy that is blocking faraway light. Well, unfortunately, that is not a potential solution because Ludwig Boltzmann showed that if that was the case, then this dust would eventually heat up to the average temperature of a star's surface and radiate this energy, and still the night sky would be as bright as a star all around. So the actual solution was arrived at by none other than Edgar Allan Poe, the famous poet and storyteller. And he believed that the universe began a finite amount of time ago, and he said that, well, if the universe is finitely old, then not all of the light from the most distant stars has yet had a chance to reach us. Now, of course, he didn't know about distant galaxies and stuff like that, but he figured that the Milky Way went infinitely in extent, and now we know that it does not, but still, this was really the first real good hint at a solution. So obviously Edwin Hubble's observations of the expanding universe aided in this. So in our discussion of extragalactic astronomy, we talked about Edwin Hubble's first major discovery, where he discovered that the so-called spiral nebulae were actually island universes, which we now call spiral galaxies. But as he studied these in more detail, as a good scientist does, he found an interesting fact. He noticed that if he made a plot of the velocities of these objects, which you get from spectroscopic data that was available long before Hubble, versus their distances from us, which Hubble determined using Cepheid variables. Now we have lots of ways of determining these distances, but Cepheid variables still figure very prominently in this. He found that a straight line provided a reasonably good fit for these data, and I'm going to show you that plot very soon. But since this gave a straight line fit, the realization is that a galaxy's recession velocity is proportional to the galaxy's distance. So even though Hubble himself was not really big into this conclusion, the actual conclusion of this, when combined with general relativity, is unavoidable. That space itself is expanding, and that carries galaxies along with it for the ride. Now, I should mention something we mentioned before in the extragalactic astronomy discussion, that bound structures are not going to be pulled apart from each other by the expansion of space. It's unbound structures that get pulled apart by the expansion of space. The fact that simply the distance between the objects ends up increasing in time if they're not bound. And we call this the Hubble flow. These are a couple of plots. The plot on the left is based on the original plot made by Edwin Hubble in the 1920s. And the plot on the right is a more modern plot showing a much greater distance scale and not really showing the closest galaxies that were in Hubble's plot. Notice that in Hubble's plot there's quite a bit of scatter. Think about it this way. Galaxies are often interacting with each other. In particular, galaxies at similar distances tend to have these interactions causing one galaxy to go toward another and another galaxy going away from each other, from the other, Newton's third law, that sort of thing. Or if that form of result might be due to tidal forces from other galaxies. But the other would be two galaxies approaching each other. And that would mean that one galaxy is going away from our line of sight, relative to this Hubble flow, and the other galaxy is going toward our line of sight relative to this Hubble flow. Now, notice you do see a few that have negative velocities, meaning that they actually are coming toward us, and a few kind of close to zero. Well, those are the ones that are closest to the Milky Way galaxy. In fact, the two that are right here are probably the Large and Small Magellanic Clouds, I would guess, and the four over here probably include galaxies like M31, the Andromeda Galaxy, which is on a collision course to us. We've discussed that before back in the extragalactic astronomy and the Milky Way discussions. And the Andromeda Galaxy's two orbiting galaxies, M32 and M110, and one of those galaxies also might be M33 as well, which actually we now realize I think is coming toward us instead of slightly going away. But in any case, when you look over much farther distances, the Hubble flow overwhelms those random differences due to the galaxies interacting with other galaxies. Sometimes you'll still have little blips like this one up here, but overall those get washed out when you average over lots and lots of galaxies. And this plot just shows a few representative galaxies. So overall, this solves Olber's paradox. Not only did this mean that the universe came into existence a finite time ago, but this also means that there are certain galaxies that are so far away from us that they're moving away from us faster than the speed of light. That does not violate special relativity. Special relativity says that objects cannot move through space faster than the speed of light with respect to some other observer at that same point. But that doesn't say anything about space itself. It's space itself that is carrying away these galaxies, these very distant galaxies, away from us at a speed greater than the speed of light. But we don't see those because they're beyond our observable universe. But we realize that they are there because we see that there are other galaxies near the edge of our observable universe. Then we make a calculation and realize that by now, because remember the light from galaxies at the edge of the observable universe was emitted 13 billion years ago, we realize that now those galaxies are so far away from us that they are going away from us faster than the speed of light. Whereas 13 billion years ago, they weren't. So, not only did the universe begin a finite amount of time ago, but space is pulling itself apart, so to speak, due to this cosmic expansion. So therefore, the night sky is not as bright as the surface of a star. So galaxies, as the universe expands, kind of ride along with the Hubble flow. Now, at first you might think, oh, maybe this is a violation of the Copernican principle. Maybe we actually are at the center of the universe. Everything is expanding away from us. But here's the thing. If space itself is expanding, which is what this observation implies, that means that anybody in any galaxy, in any place of the universe, is going to see the same thing. So let's pretend that this blue galaxy is the Milky Way galaxy, and this yellow galaxy over here is some other galaxy. Well, in the future, as the universe expands, you get something kind of like this. Things spread out more, so we've expanded apart. So to figure out what somebody in the yellow galaxy sees, what you need to do is you need to subtract the velocity of the yellow galaxy according to those of us in the Milky Way, and when you do that, you're going to get 0 for the yellow galaxy. In other words, that puts you in the frame of reference of the yellow galaxy. But for the Milky Way, instead of getting 0, you get minus that. So again, people in the yellow galaxy see the Milky Way going that way. And when you do that to all of the galaxies in this picture to see what somebody in the yellow galaxy would see, they see exactly the same thing that we see. They're just in a different spot. Isn't that cool? So what that means is that you can either say that there is no center of the universe, or that everything is the center of the universe. Like, say, your navel is the center of the universe. Great. Or that you are the center of the universe. I'm sure there are a lot of politicians who believe that. So how do we deal with this? Well, this discovery by Edwin Hubble, remember, was made in the late 1920s. I think first observations indicating it were kind of around 1926, but I think he published this around 1928, 1929. But anyway, remember, Einstein had already published general relativity in late 1915. This became well known in 1916, but he had given his field equations this extra term and this cosmological constant to prevent the universe from contracting in on itself, because he had no evidence that it was expanding. He talked with his astronomer colleagues. They said, nope, there's no evidence like that. maybe you need to fix something. I don't know whether they said that or not, but in any case, he added in that cosmological constant term. But then upon Hubble's and also Hubbeson's discovery of this, and in the meantime, the Belgian priest Georges Lemaitre had written a lot about what general relativity really implies and the fact that Einstein's solution is technically unstable in spite of that cosmological constant term. Upon the final realization that, yep, the universe actually is expanding, Einstein called his cosmological constant his biggest blunder. Not so much because it was directly wrong, but because he didn't take his general relativity theory as it was directly written down. What he didn't see is that, or at least I shouldn't say didn't see, what he refused to recognize was that general relativity predicts an expanding universe. General relativity predicts the Big Bang. So Einstein refused to believe this until observational evidence of it was found, and so he missed out on this particular discovery, in a manner of speaking. So imagine if Einstein had actually come forth and predicted the Big Bang 10 years before any evidence of it was discovered. I mean, he would have become famous. So anyway, general relativity does tell us how to deal with this, and when solving the field equations, you get something it's often called the Robertson-Walker metric. Nowadays, a lot of people give credit to a lot of the other people who are involved in this, and we often call it the Friedman-Lemaitre-Robertson-Walker metric, after Alexander Friedman, who and Georges Lemaitre, who kind of first came upon these solutions back in the early 1920s. And we're going to have more to say about Lemaitre later. But anyway, we've talked about intervals before and the Schwarzschild metric around massive objects and that sort of thing. Well, when you have an expanding universe, that changes the behavior of space-time. And what that means is that we have these kind of funny little terms in here. So it's like, okay, if the universe wasn't moving at all or doing anything at all, then you would just have this c delta t squared and this delta r squared in there, and that would be just like special relativity. But now we have this funny extra term here, this k term and this big R. You don't need to know this equation, but I'm just showing it to you so we can talk about a couple of important terms. This R term is called the scale factor of the universe. This is kind of a representative size, so to speak, for the universe. Now, do you want to know what big R is right now? Well, I can't tell you. I can also tell you it's not important what it is right now. What's important is how it changes with respect to time. How does big R change? That's what we really care about. Another cool term is this lowercase k. That lowercase k is the curvature constant. And sometimes you'll see it called kappa, depending on where you look, but that curvature constant tells you the curvature of space-time. We're going to have more to say about that. But anyway, the result of this is that as the universe expands, angles also change in a way that you might not expect. So one result of this is that normally, like as you move something farther and farther away from you, it looks smaller and smaller. But in an expanding universe, if something is really far away, it actually starts to look bigger because of the fact that the universe, at the time that light was emitted, the universe was much, much smaller than it is now, which means that object was much closer to you than it is now. And you're viewing the angle as it was seen then, as opposed to what it is now. So that curvature constant, it can be one of either three values. It can be either -1, it can be 0, or it can be +1. +1 would be like the surface of a sphere. -1 would be kind of like the center of a horse's saddle, except that it would actually have that value everywhere instead of just in the middle of the saddle, so to speak. And curvature of 0 would be like the flat Euclidean space that you learned about in kindergarten geometry. So back in the day, this K would also tell us not just the geometry of the universe, but actually the destiny of the universe and its density. So we now realize that that's not exactly the case because we made an important discovery in the late 1990s about which we'll have a lot more to say in the next discussion. But in any case, this K does tell us the curvature of the universe. And it does also tell us something about the overall density of the universe. If k is equal to 0, then the density of the universe is just right such that energy conservation was obeyed at the Big Bang. It turns out that was not absolutely necessary. Energy conservation is only required to be obeyed in events where there is time symmetry. In other words, things happen the same going forward and backward in time. But I'm sorry, I cannot think of a more time asymmetric event than the beginning of the universe. So yeah, it's not necessary for energy to have been conserved at the Big Bang. It turns out, though, that observations are telling us that it actually was conserved. So that's kind of nice in a lot of ways. Anyway, recent observations from the WMAP spacecraft, which mapped the cosmic microwave background radiation, we're going to have more to say about that later, and the Planck Observatory, which mapped it in more detail, do seem to indicate that K is very, very close to 0. Or at least if it's not 0, the universe really does behave very precisely as though it is 0. So here's a depiction of what those various shapes of the universe would look like, and how we could figure that out based on fluctuations in the cosmic microwave background radiation. If they're bigger than theory suggests, then we live in a closed universe, where it's kind of like every point has this positive curvature, and if you were to somehow magically stop the expansion of the universe, you could shine a laser beam ahead of you, and say in billions or trillions of years, it would come and hit you in the back of the head. On the other hand, if you had negative curvature, these features would be smaller than predicted by theory. But the current fact is that the features are the same size as you would predict by theory. We'll have more to say about that later. But long story short, it seems that high school geometry is correct, that we live in a flat universe. Now, what does this mean? If the universe is expanding, that means the distance between points must increase over time. So the idea is you could rewind that backward, and there would be a time when the universe was very small and very dense and very, very hot. And that must have been the moment of creation. I should mention that people were not using the term Big Bang. The term Big Bang was actually invented by Fred Hoyle, who was an antagonist of Big Bang theories. He gave the term during a BBC radio show. Fred Hoyle was known also as a great teacher. He was against the idea of Big Bang theories. A number of cosmologists in the 1940s were against Big Bang theories. They thought that the idea of the universe having a creation at some finite time ago in the past smacked too much of religion, and Christianity in particular, which is ironic because there are some fundamentalists who are against the idea nowadays. But in any case, it's something that kind of does seem to be somewhat similar to at least a non-literal interpretation of the story of Genesis in a lot of ways. And for a lot of scientists, especially during the 1940s, thought that that seemed a bit too outlandish. Observations, though, have confirmed it, as we will soon see. But anyway, the steady state theory, which was invented by Fred Hoyle, stated that the idea was that the universe had been around forever, and that instead of matter coming forth in one big bang, that was the term that Fred Hoyle used on his radio program to try to explain to people what the differences were between Big Bang, what we now call Big Bang theory, and steady state theory. According to Hoyle and his colleagues, matter was continuously being created, very slowly, and just popping into existence at random parts in the universe. Now, I will say that that might be a violation of energy conservation. The Big Bang itself is not, because, especially if time wasn't around before the Big Bang, or at least it didn't have its present meaning, then it would not have been a violation of energy conservation. But if the universe has been around forever, then that means time has been proceeding forever, and matter popping into existence would violate energy conservation. Unless general relativity is wrong. And Fred Hoyle and his colleagues actually believed that general relativity was wrong, that you needed to add a number of extra terms, what they called a creation field, to the equations of general relativity. It's a very mathematically interesting and elegant theory. I've looked into it. Unfortunately, it turns out to be wrong. So it makes a prediction that the universe is the same at all times because it's been around forever and you're just very slowly getting material popping into existence, something like 1 hydrogen atom per cubic meter or something every century, or maybe it's even much larger than every century or a cubic meter. But still, this is what Hoyle and his colleagues termed an improvement to something called the cosmological principle. So we're going to have more to say about the cosmological principle later when we talk about how we think the Big Bang happened. But I'll just tell you now, the cosmological principle says that on the largest scales, like gigaparsec scales, like if you take a giant hunk of the universe, say several billion light years in diameter. That giant hunk is basically going to be the same as any other giant hunk that you take anywhere else in the universe. In other words, the general structures are going to look the same. You're not really going to be able to distinguish anything special about one hunk compared to another hunk of the universe. That's the principle of homogeneity. Now, there's also another principle called isotropy. The principle of isotropy is that not only is the universe the same in every big chunk that you might take, but if you go to any particular spot of the universe is going to look the same on large scales in all directions. This is something that was kind of proposed in, I think, either the late 1920s or the early 1930s, as they were really getting their solutions from general relativity together and finding what these imply. And the result is that it implies a Big Bang. So these were simply taken as postulates, but it turns out that they are observationally true. In fact, they're observationally true to too good of an extent that makes one realize that it might be kind of difficult to figure out why this is the case. Again, we're going to have more to say about this later. But in any case, Fred Hoyle and his colleagues, they believed that the cosmological principle needed to be improved. They said that not only is the universe the same in all places and in all directions, but it's also the same at all times. So that if you were to look back far enough into space, back into distant times, very, very distant times, like 10 billion light years away, you would observe the same types of galaxies that you have today. But it turns out observations contradict this. In fact, we were already starting to see this in the 1950s, that when astronomers were looking at using their new radio telescopes at these things called radio galaxies, they found that they were very far away and that there were a lot more of them in the very distant universe per cubic parsec or megaparsec, I should say, than there are today. But that was just an interesting result that seemed to question the validity of steady-state theories. But we're about to hit something that completely annihilates them. So, enter Ralph Alpher and Robert Herman, and also George Gamow. We're going to talk about Gamow very soon. But Alpher and Herman used general relativity and thermodynamics and nuclear physics to show that after the Big Bang, there must have been a period of nucleosynthesis where protons and neutrons collided to make helium. Now, this is a little bit different than the proton-proton chain in stars, because neutrons by themselves are unstable. They have a half-life of something like 7 or 11 minutes, something like that. And if they're not bound to protons and nuclei, they're going to decay. But in the early universe, I mean, we're talking about seconds to minutes after the Big Bang. The neutrons haven't had time to decay much yet. So the protons and the neutrons collide, and they end up making helium. And this continues on down until you end up getting trace amounts of lithium-7, which survives today, and beryllium-7, which does not survive today because it has a half-life of 53.3 days. So none of that survived. But anyway, this results in a prediction that before the universe expanded more and cooled, about 25% of the atoms in the universe would be helium, 25% by mass, that is, and that this should generally be true in galaxies. And it turns out, not surprisingly, we've talked about this a lot in the course, the universe is about 3/4 hydrogen and about 1/4 helium and 1 to 2% other stuff in terms of the matter that makes it up, the normal type of matter. And they showed, along with George Gamow, that the expansion would, after a while, cool the universe enough that atoms would be able to form without electrons being ejected. So during the Big Bang, you couldn't have actual atoms. You could have atomic nuclei starting after about a second, but you couldn't have atoms. The temperatures were way too hot for that. Any electron that gets bound to one of these nuclei is soon sent off by a gamma ray that has way more energy than is necessary to flick it off. But eventually the temperature cools down to about 3,000 kelvins. And when you get down to 3,000 kelvins, that's actually cool enough for hydrogen atoms to form. Now it's a little more complicated than this. Helium ions actually form in the meantime, and strangely enough you actually end up getting helium hydride molecules. Helium hydride was the first molecule to form in the universe. That's kind of cool. We don't think of helium typically as forming molecules, but yeah, the first molecule ever to form in the universe was actually helium hydride. Anyway, we'll have more to say about this exact timeline later on in the next discussion, but suffice it to say that a back-of-the-envelope calculation that was done by George Gamow found that now the temperature of this original background radiation that would have been released when the electrons were able to combine with these hydrogen atoms should have had a temperature originally of something like 3,000 kelvins, but that now that would be redshifted to a temperature of on the order of 5 kelvins. Well, that could potentially be detected. In fact, there were already hints of that detection in the early 1940s through molecular transitions that were being caused by this cosmic microwave background radiation, as we call it now. But they didn't realize that that's what was going on when they made those detections back in the early 1940s, things like CNO molecules, that sort of thing. But anyway, there is this prediction that came from 1948 that there should be this background radiation left over from this Big Bang that should be detectable today. Now, meanwhile, in 1964, Arno Penzias and Robert Wilson were two scientists who had absolutely no idea what they were doing, and the result of having absolutely no idea what they were doing was they won a Nobel Prize in 1978 for this work. They found this relic radiation. They were doing completely different work. What they were doing is they were mapping the sky for Bell Labs using this horn antenna, and they found this extra hiss in their horn antenna that they just could not explain. First, they found a pair of nesting pigeons in their horn antenna and figured, well, maybe that's blocking the detector. So they removed the pigeons, let them go about 40 miles away. Unfortunately, they turned out to be homing pigeons and they had to be removed again. And they cleaned out the, quote, white dielectric material that had been left behind by the pigeons. But even after doing that, it reduced the hiss a little bit, but they still had this hiss left over that they could not explain. And this hiss came from all parts of the sky. Now, also, meanwhile, Robert Dicke and Jim Peebles worked together around this time, and they basically rediscovered the predictions of Alpher and Herman and Gamow. And the result of that was that they did a more refined calculation of the temperature of this cosmic microwave background radiation, and they estimated it to have a temperature of 3 kelvins. And they said it should be everywhere. So, this stuff should be everywhere? Okay, let's set up some detectors because we have present-day technology that is able to detect this stuff. Let's set up some detectors. So as they were getting work during that, in doing that, they got a call from Arno Penzias and Robert Wilson that they found this weird radiation all over the sky, and they didn't know what to make of it. Well, Dicke and Peebles knew exactly what to make of it, that they had been scooped for one of the easiest Nobel Prizes in history. So Dicke and Peebles did not get the Nobel Prize. Alpher and Herman and Gamow were also shafted, but it was actually Arno Penzias and Robert Wilson who got the 1978 Nobel Prize in Physics for this discovery. So anyway, talking about the history of the universe a little bit. So first, there's the very, very early universe, and then there's the accelerating expansion in the present day, which we'll have more to say about later. And I should mention that we have very, very high confidence in our knowledge going back to maybe about 10 to the minus 32 seconds after the Big Bang. So before the Big Bang, there was no space and there's no time. This is according to general relativity. The truth is, general relativity predicts itself not to be a very good theory for explaining stuff at times like this. Instead, we actually need a quantum theory of gravity, maybe something like superstring theory, if we can actually find a version of superstring theory that corresponds to our universe. But in any case, the universe did not have any well-defined forces at that instant. So that was around like 10 to the minus 44 seconds from the beginning. But then something happened, and the strong nuclear force separated and from the combined weak and electromagnetic forces at about 10 to the minus 36 seconds. This caused the universe to undergo an extremely rapid period of expansion, doubling 100 times by a time of 10 to the minus 32 seconds. So this was an incredible period. We call this the inflationary epoch. We'll have more to say about this later. And then, after about a trillionth of a second, that is 10 to the minus 12 seconds, the electroweak force separated into the weak nuclear force and the electromagnetic force. This has been experimentally verified, that at these types of energies, the weak force and the electromagnetic force do indeed combine. And that the theory leading up to that got several people Nobel Prizes, and then the experimental confirmation of that also got people Nobel Prizes. In fact, the theory leading up to that, I believe, got like the 1979 Nobel Prize in Physics for Stephen Weinberg, Sheldon Glashow, and probably Abdus Salam. And then the 1982, I believe, Nobel Prize, maybe 1983, ended up going to the people who actually confirmed that this really does occur. They confirmed it experimentally. Anyway, up until about a microsecond, 10 to the minus 6 seconds, the universe is essentially a quark-gluon plasma. So we could talk a whole lot about quarks and how they work together to combine together to make protons and neutrons and other things, but we'll leave off of that. But long story short, at very, very high energies, those protons and neutrons don't really, they can't stay together. Instead, everything gets smoothed out into this quark-gluon plasma. The gluons are the subatomic particles that communicate the strong force between the quarks and bind the quarks together. Fast forward. Up until 1 second after the Big Bang, the universe was too hot for anything to really stay together. Protons were able to form starting about a millionth of a second after the Big Bang. That's what we just mentioned. But protons could not collide with these neutrons to make deuterium. The universe was just too hot. So you had to wait for 1 second after the Big Bang. Yeah, I know that's an incredibly long period of time. Well, back then it was, because so many things were happening during those first fractions of a second. But deuterium is made starting about 1 second after the Big Bang, and then various reactions ended up leading to helium production. And after about 3 minutes, the universe cooled enough that no more nuclear fusion could occur. And at that point, the universe is composed of about 75% hydrogen by mass, 25% helium by mass, and trace amounts of lithium. Now, those various reactions that I asterisked in the last slide end up being like this. You don't need to know these. This is not something as important for you to know as the proton-proton chain. But anyway, a neutron and a proton would make deuterium, and you'd get a gamma ray. And deuterium plus deuterium would make helium-3. And remember, this is an easy reaction to occur. It does not require very high temperatures to occur. So you get a helium-3 plus a neutron, and that puts a neutron back into the mix. And you can also get a deuterium plus a deuterium giving you a tritium nucleus. That is a hydrogen-3 nucleus plus a proton. And this helium-3 plus a neutron can also give you a tritium nucleus plus a proton. Tritium is unstable. It has a half-life that means that this initial tritium that came is not around today. Its half-life is about 12.3 years for that matter. So anyway, after 3 minutes, there was no more nuclear fusion. The Big Bang created hydrogen, it created helium, it created small quantities of lithium. But by the time it was able to create all that much helium, enough helium that you might be able to try thinking about the triple alpha process, the universe had cooled to a temperature that was too cool for the triple alpha process to occur. Remember when we talked about that with our sun, the triple alpha process requires 100 million kelvins in order to occur. But by that point, 3 minutes after the Big Bang, the universe had cooled too much for that to occur. I mean, it had cooled too much even for any more fusion of hydrogen and deuterium into helium to occur. So, we're done. There are no heavy elements in the universe, and we do not exist. Well, that was initially a problem because this is one of the things that Fred Hoyle came back to, is like, haha, your theory cannot account for the heavy elements in the universe. In fact, it was Fred Hoyle and his colleagues who, like, I think William Fowler was one, and the Burbages, who actually came up with the correct theory about how the heavy elements were created. They showed that they were created in the cores of stars, and that supernova explosions also created even heavier elements, and the supernova explosions helped to spread them throughout the universe. In fact, George Gamow, who we've mentioned already, had this little version of Genesis that he wrote corresponding to this. He said something like, in the beginning, God created the elements, and he created hydrogen, and he created helium, and that he got so excited that as he was calling out masses, he forgot to call out for mass 5, and thus realized that he would not be able to form any heavy elements after that. That part of the joke goes along with the fact that there are no stable nuclei that have an atomic mass of 5, or 8 for that matter. So God, being disappointed, at first he's thinking that he's going to recollapse the universe and start again. So the story goes that George Gamow wrote. And then he said, but instead, God decided to solve his problem by a most impossible method. And so he said, let there be Hoyle. And there was Hoyle, and God told Hoyle to create heavy elements in any way he pleased. So Hoyle created them in the cores of stars, and he created supernova explosions to spread them throughout the universe. So yeah, a cute little version of the story of Genesis that George Gamow wrote, in talking about how his own theory for explaining the heavy elements failed, but how his rival, Fred Hoyle, got the correct theory, at least for how the heavy elements were created. But, as we were about to see, Fred Hoyle was wrong about a very critical aspect. So anyway, for the first 60,000 years after the Big Bang, the universe's overall density was dominated by radiation. But as the universe expands, things cool down. That radiation ends up getting redshifted, and its temperature ends up dropping. In fact, by 200,000 years, the universe was actually cool enough for helium nuclei to start to capture electrons and become helium plus 1 ions, and even helium atoms. And then, by 370,000 years after the Big Bang, protons captured the remaining electrons. That let through light. Let there be light. Because when there are electrons running around, the electrons scatter all of the photons. So you're not really going to be able to see anything in such a universe. But after that occurs, the photons are allowed to travel, and you have that light. That is the cosmic microwave background radiation that was predicted first by Alpher and Herman, then George Gamow, and then by Dickey and Peebles. But was discovered by Penzias and Wilson. So the redshift of that now has been redshifted to a temperature of 2.7255 kelvins, which is very close to the relatively rough calculation given by Dickey and Peebles of 3 kelvins. And we call this the cosmic microwave background radiation. This is the first image that was taken of this in the all sky. Now, the difference in temperature between the red parts and the blue parts is only something like 1/100,000th of a Kelvin. It's a very, very small difference. The fact that those differences do exist, though, is important, because the fact that it's there and the fact that it's black-body radiation is exactly predicted by Big Bang theories. It is not predicted by steady-state theories, but the fact that there are little shapes there is predicted by various theories about how the Big Bang happened. We're going to have more to say about that in a future discussion. This is a much improved map of the cosmic background radiation made by the WMAP, the Wilkinson Microwave Anisotropy Probe, in 2003, and then an even better version from the first full results of the Planck survey that were released in 2013. Now, this cosmic background radiation that's left over from the Big Bang, strangely enough, if you have an out-of-tune television screen, 1% of the snow that appears there is actually coming from the cosmic microwave background radiation. That's really cool. So here's a summary of what we know about the early moments. So we can actually, the universe is very old. I mean, we can see objects that are 13 billion light years away, and those objects look very, very different from similar objects today. In other words, we talked about in the extragalactic astronomy discussions that galaxies early on look very different from galaxies today. And we can also measure the ages of stars. We've talked about how to measure the ages of star clusters using the main sequence turnoff on the HR diagram, and we get the ages of the oldest stars being 12 to 13 billion years old. We also know that the universe probably began at a finite time in the past. Now, there are various scientists who have come up with, quote, alternative theories to the Big Bang, end quote, that actually state that the Big Bang was not the moment of creation. They still believe in the Big Bang. Keep that in mind. They still believe that the Big Bang was a special event, but they believe that time existed before the Big Bang and that there was something else going on then, and they try to work out various quantum theories of gravity to figure out what that might have been and come up with ideas that way. But as far as we can tell, at least to the best of our understanding, the current paradigm is that time began at the Big Bang. What we do know is that the universe started expanding really quickly at the Big Bang, and that was a momentous period in time because that was a quick expansion that resulted in somehow a creation of matter. And those details are still being worked out, but we're going to have more to say about that when we talk about how the Big Bang happened. But in any case, this ended up resulting in Big Bang nucleosynthesis. The predictions of that are very, very well confirmed by observations, especially having to do with helium abundances and other light element abundances. The lithium is kind of difficult. We have trouble with lithium. Part of it seems to be, probably has something to do with the fact that there are lots of ways of creating and destroying lithium. But in any case, we recognize that at some point in the very distant past, the universe was much hotter than it is today. That's revealed by the cosmic microwave background radiation. That is, the discovery of that cosmic microwave background radiation was basically the nail in the coffin for steady-state theories. Fred Hoyle himself admitted that as soon as that announcement was made. He basically said that his own theory was dead. He eventually retracted that admission and came up with some various other creative ways of trying to rescue it, but nobody really believed it to much of an extent. This is a graph of the cosmic microwave background radiation data points plotted on top of the theory prediction. The theory prediction is the solid line. Now, there is a cool little story that in one of the early talks about this, the plot was given, and the person giving the talk said that, yeah, you can see that the theory exactly agrees with the observations. And somebody in the audience raised a hand and said, well, why don't you actually show us the data points with the uncertainty bars on top of this curve so that we can actually see how well it agrees with observations? And the guy giving the talk said, well, we did do that, but the error bars are much smaller than the thickness of the line. And that's where you kind of get chills down your back, that this is basically the best agreement between theory and observation in the history of science. In order to make the error bars visible, they've actually multiplied them by 400 so that you can see them here. And even then, they're still relatively small. So, I mean, like, generally when you have a good theory out there and you find that observations are matching your theory really well, you wait until you hit like 3 sigma error bars before making that announcement. And you'll actually show the plot with either 1 or 2 sigma error bars. In the case of the announcement of the Higgs boson, well, that was a much more monumental discovery. They actually waited until they had it agreed to within 5 sigma, which meant that there was basically a 1 in a million chance that they were wrong in their discovery of the Higgs boson. Here we're not talking about 2 or 3 or 5 sigma. We're talking about 400 sigma error bars, and the match is still basically perfect. That is awesome. Again, it's the strongest agreement between theory and observation of any scientific theory in history. So galaxies, as we know, have evolved considerably over the past 13 billion years. Now galaxies look very mature, but in the earlier universe, galaxies looked very ragged, again in direct contradiction to theories that the universe is infinitely old or that it was created in its present state somehow. Because as you look farther back, galaxies look very, very different. The universe has evolved in time. Again, astronomy is the only scientific field in which it is possible to directly observe the past, as opposed to observing relics of the past like you do in all the other scientific fields. Here are galaxies of today, like this, pretty mature looking. Galaxies from long ago. The ones that you see here that look somewhat mature, one, they're smaller, two, they're actually foreground galaxies. They're only a few billion light years away. But the background galaxies here, when you zoom in on a lot of these, you get things that look very different from galaxies today. Why? Because they're still in the process of forming and merging and stuff like that. So, how and when did the first stars form? So, a lot actually had to happen before the first stars were able to form. 370,000 years after the Big Bang, that's when the cosmic microwave background radiation was let loose, when the hydrogen atoms formed by protons capturing the electrons because the temperature had cooled down cool enough for that to happen without them being ionized again. So we called that event recombination. And it's an interesting term because they were never combined together in the first place. In other words, you didn't have protons and electrons combining to form hydrogen atoms at some earlier time, but the term comes from particle physics, so we use it. Oh well. But again, that's the event that allowed light to go through to the rest of the universe. What we see now is the cosmic microwave background radiation, after, of course, a huge redshift by a factor of about 1100. Now, what that means is that before that, the electrons were around and they were blocking these photons. Photons love scattering off of electrons, which means they couldn't travel in a straight line. But once recombination occurred, the photons could go out and send the information about the cosmic microwave background radiation to the rest of the universe. We call that the moment of last scattering. And that's when the universe was cool enough, and it continued to be cool enough. As it kept expanding, it got cooler and cooler and cooler. And for about 100 million years, structure continued to form as gravity pulled matter into regions of greater and greater density and away from regions of lesser density. When that happens, it's as if there is a pressure in the regions of lesser density pushing things outward. So during that time, though, there were no stars around, so we call this the cosmic dark ages. Then the cosmic microwave background kept continuing to cool down as the universe expands. Remember, an expanding gas cools. So after 6 million years, it was cool enough that you would not have been able to see the glow of the sky anymore. Before that time, the CMB was hot enough that it actually glowed visibly due to the blackbody radiation that it had. And then, after 16 million years, the temperature actually fell below the freezing point of water on Earth. But finally, after 100 million years, the first stars formed. This happened when collapsing protogalaxies, which were very large clouds of hydrogen and helium, had attained the necessary mass to collapse. But these first stars were very, very massive, because since there were no heavy elements around, that meant that you didn't have things like silicates and dust particles able to radiate off that energy that was occurring in the conversion of gravitational potential energy to kinetic energy. What that meant was you had to wait for molecular hydrogen to be able to radiate off that energy. But that takes a long time. That gives time for these overdense regions to merge together, which means instead of having a whole bunch of little stars, which is what you have in big star-forming regions today, you had a few really massive stars. And these massive stars were hot enough that they very quickly combined together to re-ionize the surrounding what had been a neutral gas. Remember, it's been neutral since the moment of last scattering, when the protons captured the electrons and recombination. But now, these first stars are hot enough that they are re-ionizing. It had been ionized before recombination, then there was recombination, and now we have re-ionization. But what this meant is that a lot of these early photons that had shorter wavelengths, were captured by this surrounding gas. I could go into a big long discussion about Gunn-Peterson troughs and stuff like that. The epoch of reionization was the subject of my astronomy master's thesis, but suffice to say this was an important event, and nowadays atoms remain reionized. Why are they, or at least in the intergalactic medium, they are reionized? This was completed before the universe was about 1 billion years old, but they remain reionized today because of quasar jets. That's kind of cool, but they will remain reionized probably for at least a very long time. So after that reionization epoch, the history of our universe was based on our studies of light from distant galaxies. And the way the universe is expanded is in the spectra of these galaxies. That's how we understand what's been going on. Now let's talk a little bit about the Hubble constant. We have a lot to say about that, and we're actually going to conclude our discussion today in the middle of that, because then things get exciting, and we're going to leave off the exciting part for next time. But anyway, the Hubble constant is the measurement of the current rate at which our universe is expanding. It's symbolized by h naught, h sub 0, the rate of expansion now. If you want the rate of expansion at some other time, then you just call it capital H without a subscript, or maybe a subscript denoting that other time. The current value is believed to be about 69 or 70 or 71 kilometers per second per megaparsec. There's actually quite a lot of debate about that, but what that means is that for every megaparsec of distance away from the Milky Way galaxy, on average, the expansion increases by 69 kilometers per second. So a galaxy that's 1 megaparsec away, on average, that's going to be going 69 kilometers per second away from us. If it's 10 megaparsecs away from us, that's like 32 million light years, then on average it would be going 690 kilometers per second, etc. And as you move farther away, the faster the expansion is. And that's the Hubble constant is given by the slope of graphs like this. And again, notice that nearby you have a lot of scatter due to galaxies interacting with each other, but as you go farther away, the overall expansion of the universe overwhelms the effects of that scatter, so the effects of those interactions, so you don't see as much scatter. But the Hubble constant has not always been the same. Think about it this way. Gravity affects everything. It affects the universe as a whole. So the idea is that right after the Big Bang, the Hubble constant must have been really, really fast. And then gravity slowed everything down, and the idea is maybe gravity would be enough to eventually halt the cosmic expansion. So a few seconds after the Big Bang, it was really fast, and then it ends up slowing down. So the question is, what is the rate at which the expansion is slowing down? That's called the deceleration parameter. It's abbreviated with the symbol Q naught, the deceleration parameter. And the idea is that if the expansion was slowing down enough, which is actually what you would have for positive curvature, positive spatial curvature, then the expansion could end up potentially turning around, and instead of expanding, the universe would eventually contract. If the deceleration parameter was not large enough, then the universe would just keep expanding forever. And if it's really small, then it would keep expanding forever faster. If it's just right, which is what you would expect in a flat geometric universe, then you would expect the expansion rate to continue forever, but gradually slowing down to approach an asymptotic limit of 0. Whereas if the density is not very high and you'd have a smaller deceleration parameter, then that asymptotic limit would be a positive non-zero amount. But this was a big deal, and astronomers found that it was extremely useful to come up with a way of figuring out what the deceleration parameter is right now. Because the idea is like, okay, if we live in this universe that we think we understand, then if we know the deceleration parameter, then we can figure out what the universe's geometry is, and thus what the universe's destiny is. And that deceleration parameter is based on how much gravity is acting. Is gravity enough? Well, that's dependent on whether or not the density of the universe is large enough. In fact, the old mnemonic for that was that density equals destiny, which is great because those are anagrams of each other. So going into the 1990s, astronomers found that they were able to use bigger and better telescopes, and they might be able to use type 1a supernovae, which, remember, are visible over cosmological distances, to track the history of our universe's expansion rate, and thus determine the deceleration parameter Q naught. And the realization of this determination is actually one of the most important events in the history of our study of cosmology. It was a quite surprising result that they got, and we are going to discuss that next time.